Good morning, everybody. Welcome to our today's plenary talk session. So we will start with Viqar Husain from the University of New Brunswick, and he will talk about the effective gravitational collapse.
Can you hear me now? Yes, okay. So I'd like to thank the organizers for asking me to speak, and this is the title of my talk. Let me quickly go over what I will talk about. So first, I'll give a broad introduction to models of gravitational collapse in quantum gravity and the types of things that people have been studying. And then I will give you an explicit collapse-bound spacetime, which is a phenomenological metric. Then after that, I'll talk about some background into shock waves using an example system. And then I'll come to the main topic, which is an effective model and some simulations from that effective model, and then after that, sum up. So my collaborators in this work are sort of two different sets. On the effective models, Francesco, Jared, Robert, and Ed. And on the phenomenological metric that I'll talk about, it's Samantha Hergood and Saeed Rasku. Samantha is a grad student who will be giving a more detailed version of what I'm about to say in that particular part. Okay, so beginning with gravitational collapse in classical gravity, there are several different well understood collapse models, starting with null dust, Vadia, and its generalizations, among the first that were ever found. And then there are various particle physics models. And the particle physics models are generally Oppenheimer-Snyder, thin shells, and various variations of them and their quantization. And I want to separate that from the field theory models. And the field theory models are many. Again, I'm thinking spherical symmetry everywhere. So the field theory models are LTB, which you've heard a lot about recently, gravity with a scalar field, perfect fluids, et cetera, and typically there's a metric of this type and other variations of that metric with two functions in it. Okay, so all of these, every single classical model is described by this Penrose diagram, and I think there are no exceptions when you have matter. This is the kind of collapse diagram you get with almost no variation. Now let me come to a Penrose diagram for which there's not too much evidence. And this is the Penrose diagram from Hawking's paper. And everyone knows this diagram. And I've always regarded this diagram with some suspicion because there is no metric for which this is the conformal diagram. And of course, this is the source of so much work in the last, I don't know, 40 years or so. And of course, we know what follows from this diagram. The black hole lifetime follows easily just by a dimensional argument. So if a black hole is a black body, the temperature is inversely proportional to the mass and area is proportional to m squared. The energy loss is given by Stefan Boltzmann law. If you stick it in, you just get black hole lifetime proportional to m cubed. Just a simple argument there. And the reason I put that up is because we're going to find something different in the effective models. Okay. So some general thoughts about what should happen in general relativity. The black hole event horizon is a global classical object. So the first question to raise is, should this be sacred in quantum gravity or should it not be sacred in quantum gravity? Related point is, there's a lot of work on quantizing classical black holes. And we normally, when we talk about quantum theory, we don't really focus on a particular solution and ask what is its quantum theory. What we do focus on is we want to quantize theories, not particular solutions. So the question I would raise about quantizing just a classical black hole is it too small a mini superspace to learn anything from? Then the other main observation about what to expect in quantum gravity is singularity resolution. And the general thoughts there, intuitive ideas there are that matter reaches some Planckian density and it encounters some resistance, bounces, and the bounce can lead to several outcomes. Metastable star, which sounds like it's going to be very unstable because there'll be some resistance to further collapse. Matter wants to collapse, quantum gravity pressure resists it, so you might get something metastable, which is unstable. And then you can get repeated collapses and bounces, perhaps, because there's a bounce, matter goes out, gravity pulls it back in, bounces back out. Or you get something like black hole to white hole transitions, or something no one's ever thought of. So it's really open, but the main feature in that point is that we should have singularity avoidance. And ultimately, the kind of question that I like to think about is, what is the quantum theory of Chopwick collapse? And as you know, this classical numerical work done by Chopwick with scalar field and spherical symmetry yielded a really rich classical structure for collapse. And the question is, what's the quantum theory of that? So that's the kind of, for me, a mini holy grail of trying to understand gravitational collapse. And so associated with particularly the third point there, singularity resolution, is an idea which Abhay and others have mentioned very often, is that we should really be thinking about dynamical horizons and not event horizons. And that relates back to the first question, why should a black hole event horizon be a sacred classical object when you come to quantum gravity? Okay, so with those thoughts, I'm just going to run through I'm going to miss out a lot, but run through some Penrose diagrams that people have been discussing in various ways, and these are based on arguments, quantization of black holes, metric gluing, et cetera, et cetera, et cetera. So the first one, first detailed one, is due to Hayward, and this is from Hayward's paper in 2005, and it's a replacement for Hawking's diagram. Everything I talk about will be a replacement for that first Hawking diagram. And what he conjectured here is, with some arguments, is that there are dynamical horizons in the middle, the singularity is gone, and there's some fluxes of matter going in and out. And again, there's a heuristic metric you can construct, roughly speaking, that's done in Hayward's paper that describes this type of process. But the main thing to take away from this is there's a dynamical horizon formation, and then horizon annihilation, and then the black hole disappears. Then another paper along these lines was Viqar and Bojewald, and they conjectured another replacement for Hawking's Penrose diagram, and there's some quantum gravity region with an asymptotic region, influxes, outfluxes, and there's a discussion of this. Again, both of these diagrams, there's no concrete calculation so far that produces a metric for which these are the Penrose diagrams. So our goal is really collectively to think about that. Then you've heard a lot about black hole to white hole transitions, and here's a sampling of 3 Penrose diagrams that contain event horizons, black hole horizons, and white hole horizons. Again, the main thing about these are global objects in the space-time rather than dynamical horizons. And so, and then of course there are many other variations. If you look in the literature, lots of other diagrams of this kind. 2 asymptotic regions in one, and 1 in the other 2 on the ends. And then we come to the quantum mechanics models, and so quantum Oppenheimer-Snyder, there was some work by Munch based on the model of Ed and grad students, which is on the left, and then there was the Swiss cheese diagram, which is on the right. And so again, the point is that there's a rich spectrum of Penrose diagrams to pick from, and some of them have metrics underlying them, and some of them don't. Okay, so now I want to give you a curious little explicit collapse space-time, and this is just cooked up just to illustrate some of the features we might want in a collapse where matter comes in and matter goes back out. So there's a few curious things in here. Pointer is pointing the wrong way. So the metric is just this PG form, very simple. It's just got one metric in it. And here's a cooked up mass function, and it's this particular form. It achieves a certain purpose, as you'll see. It's got this velocity function here, and the density is given through the mass function like this. So the reason it's cooked up like this is that what this describes is a mass function flowing in, turning around, and then going back out. And the velocity determines how fast the mass function comes in and how fast the mass function goes out. And you can see in particular, one of the things I want to point out here is this parameter n here, which controls this velocity, because r minus r0 plus some vt. And it's asymptotically flat. What it describes as smooth inflow, outflow. It's asymptotically flat. It has got dynamical horizons. And as I said at the bottom, this n here doesn't need to be an integer, determines the lifetime of the trapped region. So you can, although this is just cooked up, it's not the solution to any theory. It has some interesting features that you can read off from here. So here's, oops, wrong direction. So if you look at this, there are three, this thing off. Can you still hear me? Yes. So there are three things plotted on this at different values of this time parameter in the metric. The red is the density. The green is the mass function. As you can see, the mass function is slowly moving in and then moving back out. The red is the density. It looks tiny over here, then it grows and then goes back out. And the blue is the outer trapping function. So when this hits a root, that means horizons have formed. So it forms here. There are two horizons because there are two roots. Moves in, moves back out. So that's what those two functions do, and they're cooked up precisely to do just that. And one other thing you can deduce from this metric is the black hole lifetime. And so the black hole lifetime is just measured by looking at when the roots form in the outer trapping function and then when they disappear. This is the Penrose diagram associated with it. And what we find, and this is just a fit because it's an exact metric, you find that the mass of the black hole depends on, the lifetime of the black hole depends on the mass to the power n plus 1, and n was that parameter in the velocity which determines how fast the mass function goes in and goes out. So that's what you get from the simple cooked up metric. The number of things to notice about that is is that this is PG coordinates. There's no switching of the shift function, no sign issues that you get in Oppenheimer-Snyder. Everything is nice and smooth. And so it just illustrates the points that we want to get in a quantum gravitational collapse phenomenological metric. It's got all these parameters. You can adjust them to get variance on those pictures that I showed you. Okay, now I want to switch track completely to an interlude. And this is an interlude on something called the Burger's equation. You may have seen it before. And I consider this to be the harmonic oscillator of shock waves. And there's a reason I'm presenting this, which you'll see in a few minutes. So this is a simple nonlinear equation. And it can be solved very simply using the method of characteristics, which I've just summarized over here. You take the function u, you parameterize x and t, the coordinates, with some parameter s, plug it in, and then you get the characteristic equations, which are written down here. Now, the interesting thing about this is that it has a solution for arbitrary initial data. So if you say that this function u at x in time 0 is f of x, then the method of characteristics gives a solution implicitly of this form. So f is the initial data, and the solution is given by this. So it looks of not too much practical value, but if you give me a function f, then you can actually write down the solution. You can sketch the graph of the solution. So here it is. So this figure contains two things. On the left column, you have the solution as determined by the method of characteristics for a Gaussian initial data profile. So as you see, if you just look down the left column here, the method of characteristics describes a wave that is kind of breaking, and it ceases to be a function after a certain amount of time. And this is illustrated at 3 different time steps here. So that's the method of characteristics on the left side. Now, if you look on the right side, the right column here, this is simply a display of some of the characteristics of that equation, Burgers equation, and you can see the characteristic crossing occurring. Now, on the other two frames in the right column, what you see is the corresponding weak solution to these equations. The weak solution is a solution to the integrated form of the equations rather than the differential form of the equations, and it exhibits a shock wave. So as soon as this wave starts to break, it becomes a shock, and then it travels to the right. And you can make a movie out of these things too. I didn't know how to put movies in this, so next time. So this shock wave here is numerically generated using a standard numerical method that's applied to nonlinear differential equations of the type I showed you. And the method is called the Godunov method, and that's exactly what we used in our work. So I forgot to say, if you have questions, you can interrupt me at any time. So this is the end of this prelude. So let me just quickly summarize. There's a PDE. It's got these solutions. And clearly, the left column is not suitable because it's kind of a breaking wave. So we have to look at the right side and ask, what are the weak solutions? All right, so now let me turn to what we actually did. Oops. So a similar effect arises in effective dust collapse, and there's a differential equation, nonlinear PD of the type that I showed you just now. And this is work with Jared Kelly, Robert Santa Cruz, and Ed. And there's some follow-up work on this we did, which I'll come to in a second. So the model we looked at is GR plus dust in spherical symmetry with some choices. So we have a dust time gauge, and we have an areal gauge. And so from this, we get a canonical gauge fixed action. There it is. It's got 2 degrees of freedom, this B and EB. Just to remind you what those are, there's some certain coefficients of the triad. And the physical Hamiltonian looks like this. And G is just this combination of Newton's constant and the inertia parameter. The dust density here is given by this. And the metric corresponding to these gauge fixings looks like that. Okay, so that's the model. That's the classical model that we looked at. And so now we look at this gauge fix. So here, this is very much in the spirit of the 1970s cosmological models, where you just said, okay, I'm going to fix a time gauge, like the Bianchi models with Misner and other people's work during that time, and we're just going to quantize it. So that was the approach. Okay, so now the effective theory comes from a particular type of mu bar scheme, and the passage from this classical Hamiltonian, we get this effective Hamiltonian, and from this effective Hamiltonian, these are the equations of motion. They follow straightforwardly. So the main thing is really the starting point here, which is this. Now, there are a special class of solutions to these two canonical equations, and the ones we studied were when we put EB equal to X. We put EB equal to X for a particular reason, because then we get EB dot is 0, and the only degrees of freedom left is B in this metric. So this is, in general, of course, we should be studying both equations without this choice EB equal to X, but this particular work focused on this particular choice, which leads to this equation. Now, if we make a little change of variable, replace this B, which is conjugate to this EB, then this becomes a conservation equation exactly like the Burgers equation that I showed you earlier. And so now, essentially, it's a matter of picking up this equation and turning the handle and asking, what are the characteristics like? What does it give in terms of wave breaking or shock wave, and how do we go about finding it? Okay. So what did we find? So again, just to emphasize, we're focusing now on the bottom equation here, which is a particular class of solutions to these effective theory equations in the gauge choices that I made. Okay, so here are the results. This is one particular result. We can take different types of initial data. So on the left here, we have the left column shows the evolution of a density. So we start with a Gaussian initial wave function for the profile for the density, and the frames are taken at different times. And you can see what's happening. It's moving in, bouncing back out. On the right, we have the outer null expansion function in the red line. The blue line is just a zero line to indicate where the roots occur. So here, black hole has just formed because it just touches the blue line. There are two horizons here, and actually more than one, more than two here. Then as the profile moves back out, there are two roots. And then finally, this is where the black hole disappears. And if we look further, this becomes like that. So it's lifted off, there are no more roots. So it's kind of very straightforward. Once you have the equation, you just follow a certain set of observables, and this is two of those observables. Now we can extract more information from this simulation, and one of them is this. So there are two graphs here, and the top indicates a different type of initial data profile. We looked at two. We looked at the Gaussian density profile and a tan hyperbolic profile, which is not quite like the Oppenheimer-Snyder because it's smooth and it describes a density which is concentrated near r equals 0 and slowly falls off to 0. And for both of them, what we did is we numerically determined the lifetime of the black hole, and the lifetime of the black hole essentially is determined by when the roots in the outer trapping, outer expansion function form, and when the roots disappear. And that's something we can track numerically. So in both types of initial data, we found that the lifetime of the black hole, lifetime of the trapped surface region, is proportional to mass squared. So you can see this is quite a range of masses and quite a range of lifetimes that we studied numerically. And this is a fit to it. So the other thing to notice is in this black hole lifetime, this coefficient for the two different types of data numerically determined is almost identical. T equals this 8.3, et cetera, m squared. Same thing over there. And so what we're finding then with these particular choices for this model, that the lifetime of trapped surfaces is proportional to m squared. Okay. Now, I wanted to comment on other gauges. So here's another gauge. So this LTB spacetime can be studied in these co-moving coordinates where the metric takes this form. And the LTB equations for this particular form of the metric has been derived by Christina and collaborators. And the equations they found are these for this, for R, for this function E, and for this function M. Now, the question arises, do these also lead to shock wave formation in any way? So one of the observations concerning these equations in a recent work with Francesco and Ed is that we determined that in fact these equations are in fact the characteristic equations for a pair of partial differential equations of exactly the Burgers type. And here they are, and there's some, it's not too difficult to determine. This function f here is exactly this function f here, with all this defined as f squared over r squared. And so the point of the slide is to illustrate to you that there's a possibility in other gauges also, because ultimately the flow equations follow from a nonlinear pair of PDEs of this type, which are exactly of the Burgers type that I illustrated, that characteristic crossings will occur and initial data profiles will tip over if you use the method of characteristics. And so you would have to seek weak solutions, and weak solutions are characterized by shock waves. Okay. So let me come to a summary. What we found with the way we approach this model is that the black hole ends in a shock wave. Black hole lifetime is proportional to m squared. And a further observation that if you find in your study of matter collapse any PD of this type, time derivative plus some function of u x derivative equals 0, no matter how complicated this f is, it could have explicit coordinate dependence, then chances are that you'll have to look at weak solutions and you'll find shock waves coming out of that. So ultimately it boils down to, does your system give you a set of PDs of this type or not? Now there's a lot to do here beyond the first sort of model that we looked at in the way we looked at it. Other types, other matter types, gauges, and then there's a lot of work you'll hear about which concerns covariant models. We completely destroyed covariance by fixing these gauges, so one can ask the question, suppose you take this classical theory, make some other gauge choices, do some polymerization or some other type of quantization, are you going to get equivalent results? Well, we don't know, and I think that's something, one of the things we need to investigate. And finally, a general broad point, all nonlinear wave phenomena exhibit shock waves. So why should gravitational waves be an exception, just with or without black holes? And I think that's something interesting to think about for the future, quite separate from thinking about matter collapse and black hole formation. So that's it. Thanks.
Thank you very much, Viqar, for the wonderful talk. So perfectly on time. It's 12:30, so we have plenty time for questions. I see one in the back and one in the front.
Hey, thank you on the talk. Indeed, I have two questions. The first one is that can I view your model as the generalization of the LCP protocols? I mean, can I view your model? Can I view your model as the generalization of LTP protocols?
Can it be viewed as a generalization of LBT black hole?
LTP protocol. LTP protocol.
LTB.
Yeah, can I view your result as the generalization of LTP protocols? Oh. I mean, can I view your model as the generalization of LTP protocols? Okay. Okay, thank you. My second question is that can you get the bounce?
Can you get the bounce?
Okay, thank. Okay, thank. Oh, okay, thank you. Thank you. Well,
Thank you, Viqar. This was really interesting. Uh, can you comment more on this point that you have at the end on the lifetime being m squared? In particular, I would like to understand the mechanism better. And the point that I would like to understand is in the Hawking lifetime m cube, this is m cube over h bar. And so one sees how the quantum effect arises. The inverse is linear in h bar, but here it's m square over square root of h bar. So what's the mechanism that gives you a square root of h bar? Yeah, but there's a square root of the typical scale quantum effects, so it has to be something highly non-perturbative. And what I'm wondering is what is this non-perturbative mechanism? Thank you.
Okay, I see Carlo. I see a question in the back, Madawan, and one more, Ivan.
Viqar, this was very clear. Going to strong to weak solution, the way you described in physical systems where there are shock waves, is something we sort of do understand what is going on. It's something which is not captured, but going from strong to weak solutions in physical systems different from gravity that we understand, like sound propagation in air or whatever, is something we understand. It's something that escapes the equation itself in a sense. Something else happened there and is approximated by this step of going for strong or weak solutions. So there is an element of approximation here happening. Now, my question is the following. The history of general relativity shows that often when very strange things happen in some locations, they depend on the coordinates that one was using describing that. And there are examples in which something like that in GR has disappeared by just changing coordinates. So what assures you that this, is there anything that assures you that the shock wave is not something that can be, it's hiding the fact that what is happening is something similar to the old Schwarzschild singularity or something like that, something that happens where, because the coordinates are not good for describing what is happening in that point where the shock wave forms. But we know the equations do not hold. The equation does not hold in the point where there is a discontinuity. There's some other physics that happen, right? When you're in your initial example, when the wave takes these funny forms, there's some other physics which is not described by the equation by the equation itself. So you're correcting, this going to weak solutions, a way of correcting what you physically is not captured by the equation with something else. Right. 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 But that means that the matter density is becoming high there or something like that. Right, but you don't expect physical discontinuity. You expect the density becoming very high, and so therefore other quantum phenomena coming in.
So maybe we can move on and you discuss later. So we have 3 more questions, one in the back.
Yeah, so I'm curious about this solution that the toy example solution, the cooked up solution that you have found, that you started from at the beginning. So I understand it is not an equation solution of Einstein's equations or anything, right? So, yeah. So, but I'm curious about any other properties. Does it satisfy covariant conservation equations? Does it satisfy positive energy conditions? Anything else? Mhm. I see. Okay, thank you.
Okay, then I have Ivan on my list.
So looking at that graph, I understand that you have 2 horizons, one outer horizon and an inner horizon, right? So it's a bubble horizon similar to the Hayward one. My question is that in that situation, Frolov and collaborators, and I think even Hayward, shown that there is a burst of energy is emitted from the inner horizon because of the accumulation of late null rays outside the horizon, and normally in some circumstances make the whole diagram, Penrose diagram, energetically impossible. The inner horizon emits more energy than what you had initially. So have you studied that situation here? But putting quantum fields, test quantum fields propagate. Yes, test fields on that. So right, that energy burst is coming from test fields. You have.
So one way of saying that the black hole has disappeared is what you said, right? When these horizons disappear, I mean that's the way. But can you have the Einstein tensor, right? So you have some TAP. So can you say anything about the Bondi mass? So when that's another way of, I mean, does the mass completely get exhausted when you look at the retarded time, whatever, when this thing goes, or I mean, is there a coherence of all this? It's similar to, I guess, Ivan's question. Is there some conservation going on? Yeah, but we can discuss it.
Okay, I have a very quick question. So if you can go back to the semi-classical Hamiltonian, the corrected Hamiltonian that you showed at the beginning. So that one, if I remember correctly, is obtained by a polymerization procedure. Yes. So my question is, what happens if we consider different polymerization functions or different quantization scheme? So the reason why I'm asking this, because in the Oppenheimer-Schneider model, we get compatible results. But if we use these quantization choices, so what happens if we change those choices? So if we make other choices, will we get some compatible results as well, or it does change completely? Right. Yeah, I understand. Yes. Mm-hmm. Okay. Okay, okay, thank you.
No, but if you go back to the case where EB dot is not 0, then it's exactly the same.
Okay, then we thank Viqar again for his talk.